Hello everyone, I'm Hasan Bilgili. Today I will present the fifth group presentation. Suppose that P is an odd prime and Q is equal to P to the R for some R positive integer. We mainly trace the number of the zeros of Artin-Schreier type curves as stated in here. Mostly we focused on the supersingular Artin-Schreier curves, and we assume that C is a projective smooth and absolutely irreducible curve. Firstly, I will give the definition of supersingular curves. The Weyl numbers of C are defined as the root of the reciprocal of the L polynomial of the curve, where L is the numerator of the zeta function of C. We say that C is supersingular if all Weyl numbers of C have the form in that, where zeta are from are roots of unity, and I is between 1 and 2g, and g is the genus. The smallest positive integer as C, such that eta I power s is equal to 1, is called the period of C. Firstly, we had a result, but before that I will give the tools of it, tools that we use to obtain the result. Linearized polynomial with coefficients in an extension, a polynomial of the form in that, with coefficients in an extension field of fq, say fq to the m, is called q polynomial over fq to the m. Observe that L is a fq linear. This is because that terms are x to the power cube to the power I. And for supersingular curves, we had a reduction theorem. Generally, it says that if you want to calculate the number of zeros over f to the qn, you can reduct it in a smaller field. So, as it's stated in here. Now we have the quadratic forms. It is well known that the function from fq to the n to fq, such that x going to the trace of x times lx, is a quadratic form over fq. The number of zeros of such a quadratic form can be written as in this formula, where lambda is equal to -1, 0 or 1. Suppose that w is the dimension of the radical, I mean this, and we assume that q is odd. I have to say that the dimension of radical of q has a slightly different definition for even characteristic. Note that if n and w are have different parity, then lambda has to be 0. This is because that for this formula we need output as a natural number. However, if they have different parity, this will be odd, and there is some meaningless thing. So lambda has to be 0. And one of the main tools is fiber products of Artin-Schreier curves. Consider curve over fq to the n. For an alpha from the multiplicative group of fq to the n, we define h alpha as the elements from the fq to the n, such that trace of alpha times x is equal to 0. Then h alpha is additive subgroup of fq. This is because of the definition of trace. We can view h alpha as a subgroup of automorphism of C. And for fiber product, we only need the q to the n minus 1 divided by q minus 1 many alpha. For y alpha as fiber product of y plus gammas, we have that C alphas, and the theorem that says that the Jacobian of the curve is isogenous to fiber product of Jacobian C alphas. I have to say that alphas are representative from the cosets. Therefore, the L polynomial of the curve C is equal to product of L polynomials of the curves, and we have a theorem which is useful to calculate the rational points of the C over fq to the m. Okay, in our work, we face with the polynomial x to the t minus a, and we want to understand when it factorized and when it's not. First theorem states the first theorem characterizes the irreducibility of this polynomial. So it is the following: x to the t minus a, by the way, a is from fq star, is irreducible if and only if the following two conditions are satisfied. Each prime factor of t divides the order of e of a in fq star, but not q minus 1 over e. Secondly, we have if t is equivalent to 0 modulo 4, then q is equivalent to 1 in modulo 4. Now, if we take q to the q is equivalent to modulo 4, then q has to be in that form where a is bigger than or equal to 2 and u is odd. Suppose that first condition is satisfied and t is divisible by 2 to the power a. We write t is equal to b times v, with b is equal to 2 to the power a minus 1 and v is even. Then x to the power t minus a factors as a product of b monic irreducible polynomials in fqx of degree t divided by v, which is equal to v. Now, we had this factorization where cj's are roots of it, and all roots are in fq. And first, I have to say that in the factorization, we do not need, mainly focus on what are the factorizations are. We mainly focus on what is the degree of the factorization, because all of the parts, we have the same degree in the factorization. Now, our result is counting the number of the rational points of the curve as stated in here. Actually, some of the articles, they have done it, but it has a lot of cases. But we reduced it in a short proof. So also in these articles, we have q instead of p. And we did it by finding the cardinality of that set for each beta. One of the next aim is to find the rational points of the curve, as stated in here, where a, b, c are from the fq to the star, and k is positive integer. These are references. Thank you for listening.